Morning. And shut your laptops. I still like to see your name tags because I don't know what Asmita is called or what Rucha is called. I really don't know your names. I think Marlies is the only person who still has the original name tag. Here's Pawan. Okay, let's begin, folks. Everyone, calm down. First, some of you are probably going to be fasting for the next month. Our best wishes to all of you. The class is going to be right at the same time, so I don't know how you guys are going to deal with it. But if you have any issues just struggling through class in the next month, let me know, right? We're going to continue talking about sequence-to-sequence models and attention models. We know what the situation is. A sequence-to-sequence model is a model that converts a sequence of an input sequence of vectors or symbols to an output vector sequence of vectors or symbols. And the specific version that we were looking at was one where the output may not have any apparent correspondence with the input, neither in terms of length, nor in terms of order, nor even in terms of vocabulary. So, for example, in a machine translation model. And we saw that the kind of model we'd use for this was the delayed sequence to sequence, where the entire input was first analyzed. And then once the input was analyzed, the representation that you got when the complete input was processed was then used by a decoder. So the analysis module was what we call the encoder. And the final representation was used by a decoder, which to generate the actual output sequence. And again, in this kind of situation, we use machine translation as an example, but this is endemic to this model. The output at any time did not directly depend on the outputs at previous times, and that we saw was a problem because there should be a dependency. And so we changed the model to make it autoregressive. What we mean by autoregressive is a model where the output goes back to the input. We have seen autoregressive models several lectures ago when we looked at Knox networks. So this kind of sequence-to-sequence model, in these kind of sequence-to-sequence models, the output is generally autoregressive, but the output goes back to the input. Nonetheless, the idea is very clear. If you had to perform machine translation, you'd have the encoder analyze the entire input until it saw the end of sequence symbol. The representation that it got at the end of sequence symbol was the one that would be used later by a second recurrent network, which would then use it to generate the output. And specifically, the manner in which we saw the output being generated was recurrent. If the initial start of sequence symbol would go in along with the hidden state. And at each time, a word was drawn. And because it's autoregressive, the word that was drawn went back into the system as input in addition to the recurrent hidden state itself. And thus was the final output produced. So in all of this, which is the critical component of this entire model that carries information from the input to the output? The little red box, right? So we had the encoder, which was a recurrent network, a recurrent structure that extracts the hidden representation. And then you had a recurrent structure that utilizes the final hidden state right there to generate the output. And the problem here was that all of the input of information about the input sequence is now being thrust into that one little vector over there. And so this one vector is going to be overloaded with information. Now, what did we observe when we were actually performing recurrence through an input? As you got further and further away from a specific input, there was more and more for this to store. And so information about the distant past actually ends up being diluted. And so there's some kind of mishmash, a combination of everything that's happening in there, where something in the distant past is probably much less represented than something that was immediately behind this red box. Now, on the other hand, if you actually look at, say, the machine translation problem, each one of these hidden states carries information. And at any time, the hidden state not only carries recurrent information from the past, the most of the information that it carries is about the latest input, because that has the dominant effect at the latest time step. So for example, if you looked at the fourth hidden state vector over here, that's going to be dominated by the word apple. Although it has something from the past, it's going to be dominated by the word apple. And so when you get to the end, that final red box is probably dominated by the end of sequence marker, which is why we saw that it made sense to flip the input left to right for us to do a better job of decoding, right? And if you actually look at the output, each word in the output actually has a more distinct dependence on a small subset of one or more symbols in the input, and not on the entirety of it. When you're trying to overload all of the information into the little red box, that the vector in the final hidden vector on the encoder side is diluted in some sense. On the other hand, if I want to translate, if I look at the word Apfel in German, that has the most direct dependence on the word apple on the input, right? So you want it to, or for example, the word ish goes back to all the way to the beginning to the word I. And so you would like to have some kind of a representation from the encoder side, which gives reasonable representation to every single word in the input, and not merely this overloaded vector at the end. So what would be the simplest way of getting some representation which carries information from all of those hidden states? I can just have an average, right? If I took an average, you're combining information from all of those states. And so you could just have this average, and this average can now go into the decoder. When I do it in this manner, I'm actually, instead of having the encoder and decoder be connected in this manner, I'm separating the encoder and the decoder. The encoder's job is now just to compute these hidden representations. It's still recurrent. I would compute an average of all of these hidden states, and this average now goes into the decoder, and it's being presented as some kind of a context to the decoder. So the decoder now is actually just a standard language model. It's a language model generating a word sequence with one extra variation. That red vector is carrying some conditioning. It says generate a word sequence which somehow characterizes whatever information is coming down this red arrow. So this kind of makes sense, right? But then the same average is being used to generate every single output. So it doesn't matter whether you're trying to generate the word apple or whether you're trying to generate the word gegessen, you're just looking at exactly the same conditioning variable coming inside. which is fine for a short sentence of this kind, because for a short sentence of this kind, that average probably carries enough information about every word. But then if the input word is a sentence where, let's say, 100-word run-on sentence of the kind that some of our politicians like to produce, then that average vector is going to not really be very representative of any particular input that went in. And so now this simple framework will not work. So in this situation, what we would like to have is to have a different weighted average of the hidden states for each output word. So the first word over there, when you're generating the first word, ish, you're still going to be looking at a weighted, an average of all of these hidden states. But the average is, it's actually going to be a weighted average. And this weighted average is going to be specific to the 0th output. So the 0 in the parenthesis says that this is the set of weights that you will be using when you're generating the 0th output. And then for when you're out producing the next word, you're still going to be taking a weighted average of all of these guys. But the set of weights that you have over here are going to be specific to the second word, or the word with index 1. So the weights here are specific to W1, which is being generated. And then at the next time, once again, you'd be taking a different weighted average, but now the weights are specific to the third word and the fourth word and the fifth word and so on. So we're still using the same kind of structure that we had in the past. The one key step that we took was that instead of depending on just the final vector on the input side, we're looking at all of them. And the way we are doing it is we're taking a weighted average of all of them, which was a simple first step to do, but then we're going one step ahead logically. And we're making the weights specific to the particular input that is being generated. And this would kind of work if we had some mechanism to produce weights that magically focused on the right portion of the input. So for example, if I'm trying to just produce the word upfell on the output side, I should get a weighted combination of the inputs that somehow focuses on the hidden state corresponding to the word apple, because that's what corresponds to upfell on the output side, right? So we want the weights to somehow learn to be capable of focusing on the most relevant portions of the input to generate any particular output. And how can we do this? These are what we call the attention weights. These attention weights are dynamically computed weights, which are computed as functions of whatever information the decoder has at any time. And the idea being that if this function and the decoder do work in a reasonable manner, then the weights should somehow automatically focus on the appropriate portion of the input. So how could we compute these? Now, let's say I'm trying to generate this word. So I'm out here. And so this is the computation I would like to perform. I need to use information that I have available to me at that time to compute the attention weights. What is the information I have available to me when I'm computing the element of the far right corner? What information do I have available to me at that point?
All the words before. All the German words before, as well as all the.
So all the German words before, but yes, as well as?
All the encoder states.
All the encoder states. So right there, if I want to see the most compact bit, then the information, anything that's going into the network at that point, including all the words. So if you're just using the simple recurrent word, then the word einen is the only one that's going in, right? And then the hidden state S2. So if you were trying to, I'm always missing chalk. If I were not complaining about chalk, the class is not complete. Anyway. So at that point, you're probably going to have some network which has the previous word, right? And something that came in from here. And now you're going to be feeding in a context from the decoder side to the from the encoder side to the decoder side. And that context must be computed as a weighted sum of the encoder states. And you can use anything available currently to compute that context vector. So for example, if my context vector were going in here, I could use this hidden state. If my context vector were going in here, then the only information I have is the word einen itself, right? And if the context vector were going in here, then I could use something that comes here or something that comes from here. The point is, you can use any information that is available to you when you're performing your processing to compute your context vector. That making sense, right? So because these have already been computed. Now, in our case, I'm going to assume that S2 is what is available to you. This is just for illustration, but you can always generalize from here, okay? Yeah.
The S-1 in the diagram, is that the last hidden state from the encoder?
We'll get to that. Okay, so given that, then this means that I can compute my weights for all of these guys as a function of this term, which is all of the information that I have currently available. And so my weights are going to be, in order to generate the ith output, the specific set of weights that I would use to combine these guys are going to be a function of the hidden states here themselves and the information S2 on the right. So the weight that I'm going to have, for example, for H1 is going to be a function of H1 and S2. That making sense to everybody? Questions? Right, okay. But then I want to impose a second requirement. I want the weights to sum to 1. If the weights were arbitrary, as the input got longer, I would be accumulating more and more information in the context vector. The value of the context vector is going to depend on how long the input is, which can be highly variable. So you don't want that kind of a representation. You want something that's more stable. And so you want all of the weights to sum to 1. And if the weights sum to 1, the weights will form, you want the weights to be positive and sum to 1, so they form some kind of a distribution, a probability distribution of sorts. And ideally, those weights must peak at whatever words in the input are most relevant to the current output. So for example, if you were computing the word, trying to produce the word apple, then the weight for Apfel, the word for apple, must what have peaked, okay? So, but this guy here, this function, doesn't guarantee that. If I just say that the weight is some function of hi and sj minus 1, that's a generic function. There's no way of ensuring that it forms a distribution. When I give you a collection of numbers and I want you to convert it to a distribution, what is the most common technique to do this? Just put them all through a softmax, right? So you exponentiate them. So now all of them are positive, regardless of whether the value itself was negative or positive. And then you normalize, so the whole thing is actually going to sum to 1. That's a standard softmax, right? And so the computation of the weights is a two-step process. In the first step, we are going to compute some function of this hidden state and whatever that we've got, whatever information we've got, in order to compute the weights. And the function g can be unrestricted. It can be anything. You'd get one value for every input hidden state, encoder hidden state. And then you'd put the whole collection through a softmax, and you're going to get a distribution which represents the actual set of weights. And those are the weights that you're going to use to average the hidden states on the encoder side. First one. Okay, 10 seconds, guys. This is easy. There's no internet?
Just check the today polls. Just search for the numbers.
1019, 1020, and 1021. Okay, the next poll is 8, right? But okay, can you answer these questions? The first one, is it true or false? Right, so the attention framework computes a different context vector for at each time. And what does the difference arise from? The weight, it's computing a weighted average of the encoder hidden states, and these weights are different for each output, right? The context vector is chosen as the hidden encoder representation of the input word that is assigned the highest attention weight. True or false? True or false? Okay, why is it false? You're actually taking a weighted average of everything, right? You're not just picking the most likely. And then the attention weight to any input word is a function of the hidden encoder state representation of the word and the most recent decoder state. It's true the way I've defined it, but if I actually go back to the way I have it on the board, it could be a function of more than that, right? Whatever information you've currently got available. Anyway, so we are good with understanding what we have over here. There's one small component left to understand. What is this function G that takes in the hidden encoder hidden state and the decoder state and computes the raw weight, which is going to be put through the softmax. And there are a variety of options over here. If the hidden states on the input side, on the encoder side, H, are the same length as the hidden states on the decoder side, then you could just take an inner product between the two. And that's going to give you a scalar for every input time, right? And you could put those scalars through a softmax. Now, if the two vectors are different lengths, then how do you compute an inner product between two vectors that are different lengths? Yeah.
Do we basically like apply a window approach?
Or
We can use the matrix
extra zeros to
yeah, you can.
we can use the matrix to project one.
So you can actually use an intermediate matrix, right? If I'm multiplying, I'm trying to compute an inner product between a vector of length 4 and a vector of length 2, then I can have I can make it a matrix inner product where the matrix projects it's a 4x2 matrix which projects the vector of length 4 down to a vector of length 2, and then I can compute an inner product. So that would be something like this, the H transpose WS, which is on the second line. So this is what you would do if if the two vectors were different lengths. You can also have other more ugly functions. People have tried throwing in tan H's, simple perceptrons, MLPs, what have you, and it all works, yes.
Professor, doesn't it mean if we project it down that we lose some information?
Which is fine, right? They're different sizes. So yeah, again, remember the weight is, you're projecting down only for the purpose of the weight. The final context vector is the same length as H.
Yeah.
So you're not losing information from the context itself, yeah.
Why can't we project up the shorter length vector?
You could do it the same way. Eventually, it's going to be the same thing. The subspace is going to be, the dimensionality of the subspace is going to be the lower of the two, right? So yeah.
Is there a reason that you didn't consider the anything in the function? You said like you can use that also as part of it, right?
So you can use pretty much any information that you've got. It depends on where you're feeding in the context vector in your decoder side. If the context vector is going here, in here, you have no recurrent information at this point, correct? If the context vector is going into the hidden state where the recurrent information is available, you could be using this or this. If the context vector is being fed in at a higher layer, you could just be using this hidden state. So it depends on what you're looking at. This is just a simplified illustration, okay? So anyway, let's see how this would work. Let's consider a typical conversion process, assuming the vector in a product to compute the raw weights. Again, the raw weights must be scalars. You would get one raw scalar weight for every input hidden state, encoder hidden state, and these are going to be soft maxed into a distribution, and that's going to give you a set of scalar weights which sum to 1, and you'd use those to compute the weighted average of the H's, right? So if I had an input, I ate an apple, it's terminated by an end of sequence, so that's, you always need the EOS, otherwise you have not completed processing the input. If you put it through the recurrent network, you're going to get one hidden state at each time for each input. And then what was S of -1? There are different ways of coming up with S of -1. You could just average all of the H's and call that your S of -1. Or you could just make it some down projection or up projection of the average. Or you could just set it to be a bunch of zeros or a bunch of ones. And pretty much all of these will kind of do the job. And that S of -1 and any other information you might have is going to be used to compute the raw weights on the input side, on the encoder side. And from the raw weights, you'll be computing you'd put them through the softmax and get the actual attention weights. Then you'd use those weights to compute a weighted average of all of the encoder hidden states, and that's going to give you your context vector. The context vector and the start of sequence symbol. Because at the first time, what is the very first word of any sequence? It's all symbol of any sequence. It's the start SOS. So the context vector and the SOS would go in, and the output is going to be a probability distribution over words, right? And now this is like language generation. From that distribution, I'm going to randomly sample a word or draw a word and using some logic. And then this drawn word is going to go back in. And now for the next time instant, I'm going to be computing attention weights, except for the attention weights, I'd be using these H's and this S0 over here in my vector in a product, in the matrix in a product, to compute the raw attention weights. And those raw attention weights would then be put through the softmax to get your actual attention weights at each time. You'd compute a weighted average of all of your input hidden states. And that's going to give you a new context vector. And so that new context vector and the word H that I've drawn as an illustration, those would go into your decoder at the next time. And you'd get a new probability distribution over words from which you draw the next word. And that next word and the hidden state S1 are now going into go into the computation of the raw attention weights from which you would get, to which you'd apply a softmax and get the actual attention weights again, which you would then use to compute your context vector. And the context vector, which is going to be different for the third word, right? And the word harbor, in this case, they're going to go in, and then you get the next distribution. So you'd continue this process, drawing a word at each time, using the latest decoder state to compute the attention weights, and using those to compute the context vector, and then passing the latest word that you've drawn and the latest context vector in to generate the next output. And you'd continue this until you actually got an end of sequence marker as your drawn output word. So the process is simple. There's nothing particularly complicated about this. And this is a very, when you follow the logic, the step-by-step approach that we took makes it obvious that this was the only way we could have actually progressed down this chain. That we needed the delayed generation model if you wanted to do a generic sequence to sequence translation. But if you wanted to extend that to actually figure out which portion of the input to focus on to generate any output, then the attention model was probably the most rational way of doing it, right? So this is the entire decoding process. I can make, now this is kind of simplistic. And the simplistic goes back to some of the questions that some of you asked. If the vectors are different lengths, why do you want to down project? When you're down projecting things, are you not losing information, et cetera, et cetera. Now, the kind of information you want to derive from H to decide how important it is for the generation of any word in the output can be different from the information that you actually want to pass to compute the output. There are two different things going on. You had the hidden state, and then you had the attention weight. The attention weight was what decided the importance of any given hidden state to the decoding, right? And the amount of information required to compute the attention weight may be very different from the information that you're actually passing to the decoding. So a standard trick over here is to have this thing query value mechanism, where this hidden state is projected to some dimension using a matrix WK, and it's projected, and this is called the key, and it's projected to a different vector V using a different matrix WV. So now we have derived 2 vectors from it. And on the decoder side, whatever hidden state that you've got to perform the generation, that too can be projected down to some dimension through some matrix. So the projected down version is what we call the query in this case. The query is what is used against all of the hidden states on the encoder to decide how important each hidden state is. And that query is combined with the key. And so the actual raw attention weight is now computed between the query and the key. And the model over here is that the amount of information you want to derive from the hidden states on both sides to decide the importance of any hidden state, that's probably resides in a lower dimensional space than the actual information that you're passing over, which is the value. And so the query and the key are going to be used to compute the attention weights. And those attention weights are then used to average the values. And the average value is what is passed in as the context. So the special case that we saw earlier was where these down projection matrices were all identity matrices. So the query and the key were both, and the key and the value were both just the hidden encoder state. And the query was just the hidden decoder state. So I'm going to continue using this for my illustration, but the more generic representation is of this kind. Is this making sense to everybody? Okay. So what is the process of decoding? Again, what are we trying to do? This is exactly the same problem that we had earlier. We are producing, this is like language generation, right? At any point, the latest probability distribution is conditioned on the entire input and all of the words that have been generated so far. And so exactly as before, each of these y's is a probability distribution over all the words in the vocabulary given the entire input and all of the words that have been output so far. So each of these y's is the latest p of yt given the entire input and y0 through yt minus 1. So if I just multiplied the probabilities of all of the words that have been output as computed by the network recurrently, that is actually going to give me the probability of the specific sequence of words that was output. I'm not going over this in detail because we've already seen this before, right? It's exactly the same problem. But now the problem that you're faced with is that of finding the most likely word sequence. Again, remember, when I'm trying to perform something like machine translation, I tell you I ate an apple. The question you ask the model is, which is the word sequence in German that most likely represents this word sequence in English? So you want to pull out the most probable German sequence given the English sequence. And so you want to pull out the word sequence for which this product is largest. And again, as before, just pulling out the most likely word isn't going to necessarily going to do it. So we're going to use beam search yet again. You're going to explore the entire tree of hypotheses. And then having explored the entire tree of hypotheses, you'd pick the one hypothesis that was most likely. By hypothesis, I mean a hypothetical output word sequence. So if I were considering German word sequences, there's an infinity of German word sequences. Given my model and the input, I would compute the probability for every one of these word sequences and pick the one that was most likely. But then there's an infinity of them. So we have to be a little, be a little careful in how you compute it. So let's say I've actually performed my encoding over here. I have the encoder and I have the original hidden state. On the decoder side, I have my S minus 1 and I have my initial startup sequence marker, S of S. So using that, I can generate a query, I can generate attention weights, I can generate a context vector. So this context vector can now be fed in. and it's going to give me a probability for every possible word in the vocabulary. Every one of these words can now be, I can make as many copies of the decoder as the number of words in my vocabulary, and then every one of these words can be fed in to each one of these copies, except this is not a very efficient thing to do. So I'm just going to keep the copies corresponding to the most probable k words, where k is the beam width. Then from this, once again, for each one of these, I can now compute a context vector. And the context vector is going to use as a query the hidden state at the previous time, right? And maybe the latest word. And so for the context vector on top, if I were going to use information from within the decoder itself, it's going to be whatever hidden state was obtained with he as the input. For the one at the bottom, it would be whatever hidden state was obtained with the as the input, for instance, right? And then using those, in both cases, I'm going to compute a context vector. And the context vectors might be very different for the two cases. Those go in, and from each of those, you'd get a probability for every possible word. Once again, you can make as many copies of the decoder as you have words on top and words on bottom. So if my vocabulary were 100 words, I'm going to get 200 copies of the decoder, and I'd only retain the k copies for which the probability was highest. And once again, the way you would compute the probability is the product of all probabilities down the path to that point. And we saw why this must be the case, right? And now each one of those in turn, depending on whatever the latest word fed into it is going to obtain a different context vector from the encoder side. And so the context vector and the latest word would go in, and you'd get new outputs, a new probability distribution at each point. So you can keep expanding the k remaining paths and pruning out everything that was too unlikely until you eventually end up at a path that for which the output is an end of sequence marker, and the overall probability of the path exceeds that of every other surviving path. If the overall probability is lower than that of other surviving paths, then that's just a natural termination, but you're going to continue extending the others till you end up with a complete sequence that terminates in an end of sequence marker, where the overall probability of the path is the highest overall, right? So I sort of went through it in words, but the concept must be clear. Does that make sense to everybody? Any questions? Yeah.
So Professor, every time as we go forward, we'll be computing a new context vector with different weights every time.
Yeah. And for every copy of the decoder, in fact, in your B.
So at he and the, we computed a different context vector with different weights. Then as we went to nose and the different nose, again a different.
Yeah, because at every output, we have a different context vector, correct?
Okay.
Yeah.
Every output mean only the top k.
Yeah, the ones that you've retained, yeah.
The beam width hyperparameter or something that is learned.
It's a hyperparameter. The wider it is, the slower your system's going to be, right?
Oh, why would the two red lines go up and go down like different?
So if you were looking at here, for example, then if nose and nose were the two words going in, so look at this. What is the previous state here? For this entry, the previous state, hidden state was this guy, correct? For this entry, the previous hidden state was this guy. And this entry also got this word, and this one got a different word. If I use some function of those as my query, the attention weights are going to be very different, right? So you get different context vectors on each branch. Any other questions? No. Okay, yeah.
So for the decoder, when we're decoding, so there will be a hidden state which is passed forward for the decoder itself, and then there is a context that we are calculating.
Correct.
So we like use both of them, just the context, average them.
There's the recurrent hidden state and the context, yes.
Yeah. So
And the word.
So we will be using both the context as well as the hidden state.
The hidden state and the word, the latest word that has been generated, right? Yeah.
Professor, this hidden state and the context vector, they are added with the affine function as we had seen before, right? With different weights again.
I'm not clear.
So Wi of hidden state plus another W to add the context vector.
So are you speaking of computing attention weights, or what are we speaking of?
The attention weights for, let's say, for
So the context vector over here is going to be a weighted sum of all of these guys, correct?
yeah, correct.
And the weights are computed using this hidden state and any function of the input,
Okay.
right? And that's where, using the matrix inner product to compute the raw attention weights and then normalizing this came in. Yeah.
It's an architecture kind of question. We only use IA and Apple example, but what if we have, how do we have the longer inputs?
The same mechanism still holds, right? Nothing changes. High 8 and Apple is all I can fit on my slide. I could fit if I had a long slide, then I'd give you a 10-word sentence. But the same thing would hold, yes.
If this beam first, have we actually used in production? Suppose we have generally, if your vocabulary is all the English words, then there will have at least 3,000, and you need to fork 3,000.
So you want explicitly, so here is the thing, right? I'm showing you a bad picture. When I'm computing the probability of this path over here, the probability of this path doesn't need this processing. If I just know what this word is, I already know the probability of the path. So you can prune before you expand your network up. At each point, you'd only be creating as many copies as the beam width. Yeah. So to be completely accurate, over here, I have, for example, I, he, we, the, right? I don't need to make 4 copies of the decoder. The probability I'm considering is the probability of I, the probability of we, the probability of he, and the probability of the. So I could have pruned before I grew the decoder. This is just for illustration. That makes sense? Yeah.
This might be a premature question, but this is with a very strong assumption that you have one sentence and you're translating it to another sentence. Is that assumption doesn't necessarily hold true. It would maybe for longer sentences, the translation might be split into 2 sentences or something like that. Doesn't that happen?
You're the first person in 4 years who's asked me that question, right? It could happen, and it would have to deal with the sentence itself. So our end of sequence marker is an end of sequence. A period is not an end of sequence marker, right? So yeah, it gets taken care of. Anyway, so what does this attention weight itself learn? At each point, you're computing some weighted combination of the input hidden states, right? So those weights, we said, must somehow learn to focus on the appropriate portion of the input. What do they actually end up learning? So here are some pictures from the first paper on this attention-based translation model. This was a translation from English to French. And so if you had a one-to-one correspondence between the English words and the French words, then you'd expect the attention to just pick up the specific English word that was most relevant for each French word. So in this picture, every column is showing the attention weights actually every row is showing the attention weights for every one of the English words in order to generate the latest French word. The French word is shown to the left. And the attention weight itself is shown as a grayscale. So the darker it is, the lower the weight. The lighter it is, the higher the weight. And so you can see how the attention weights, when the network is trained properly, you can see how the whole thing works really nicely. The agreement on the European Economic Area was signed in August 1992, period. So again, period is part of the vocabulary over here. So can somebody pronounce French over here? Anybody? Yes, okay. Can you read the one to the left?
L'accord sur la zone européenne, économique européenne a été signé en août 1992.
Okay, so whatever he said, right? But here's the thing. This first character L, however he pronounced it, maps to the. And you can see the attention for the turns out highest. For accord, it just signs up with, it peaks at agreement. For sur is it peaks on. It's all perfect. Until you get to the European Economic Area, when you go from English to French, the order is flipped. So it's the European Economic Area becomes Zone Économique Européenne, which is in the reverse order. I don't know if I pronounced it right. And so you can see that the attention weights actually flipped. And so when you're saying zone, it actually peaked on zone. For European, it peaked on European. And economic, it peaked at economic, except, now at that position alone, the attention weights are locally, have the inverse slope. Or if you look at this one to the right, for instance, it says of environments, and environments actually becomes 2 words in French. And so you can see for both of them, the attention weight peaks at environments at the bottom. So the attention weight actually magically learns to pick up the key characteristic of the input. And there are some more translation examples, which I will not attempt to read. But those of you who know French will probably see that the translation is pretty good. You'll have to confirm for me, Ivan. And those of you who don't know French will have to believe him. Okay, yes.
I'm not sure if this is a relevant question, but in this particular experiment, were the embeddings of the words learned at the same time as you were learning?
Okay, so nice question. In these, I believe over here they actually used pre-trained embeddings, but I may be lying. So go back and check the paper. But in general, you're not going to be working off one hot vectors. The output is one hot, but when it goes back into the network, you're always working with the projected down embeddings on both sides. And in fact, the projecting matrix may be different on the encoder and the decoder sides because they could be completely different languages, right? So we've seen how a trained network can be used to compute the outputs. You convert one sequence to another. But now let's consider the other flip side of the problem, which is training. So now, here's how you would do this. You'd be during training, you're going to be given an input and a target output, right? That's standard. So if you were now there are 2 different ways of doing this. In the forward pass, remember how we trained the language model. How did we train the language model when you're trying to train a language model?
We have a sequence of inputs and a sequence of outputs.
So when I trained the language model, how did I use my training data? Yeah.
Mask out everything after the current word that you're trying to learn, because you obviously don't have that information yet, and that you can produce that mask.
So you actually gave it the actual sequence of words, and you are always trying to predict the next word. And what did we call that kind of learning? What were we performing? We were doing what kind of estimate? I said it was a statistical model.
Maximum likelihood.
We were performing maximum likelihood estimation, and this was the correct thing to be doing, right? So if I follow the same format over here, this is no different from a language model. On the decoder side, you have exactly the same as your standard language model. The only difference is that now the generation is conditional. So in addition to actually just using all the previous words, you also get this context from the input. And so what you would do is this, you just pass in your input, but on the decoder side, you actually give it the ground truth labels, and it's going to obtain the context from the encoder side. And at each time, it's going to be generating a probability distribution, and you end up with a sequence of probability distributions on which, against which you can evaluate your target outputs. And then you'd get your cross entropy loss or log likelihood. You'd maximize the log likelihood or minimize the cross entropy loss is the same thing. And you can train your model. So that, because that can be differentiated and those derivatives can be passed backwards and passed through the network. And the back propagation is also going to update the parameters of whatever attention mechanism that you might have. In particular, if you're using any matrix inner products with the keys or the queries, then those matrices can also be learned. Now, this differs from this. In fact, this approach in fact performs maximum likelihood estimation of the model. there's something funny about this whole process. When you think of training a standard neural network, when you're training a neural network, what do you do? What do you pass in? Typically, at the input to the network, what do you pass in? How are the labels used?
Only use that criteria.
The labels are only used to compute the loss, right? So in your standard over here, this is not standard training. You're given the input, you're given the target label sequence, you're passing both in. And then you're getting some output and you're comparing it against the target label sequence to compute the loss. And that loss is being used to generate the entire, to learn all the parameters of the model. So you've got this ugly setup, but the decoder here is actually taking in the ground truth labels during inference. Remember, the forward pass of training is just regular inference, right? And the decoder here is taking in the ground truth labels. So this is what you've got. You're taking in the English sequence, you're taking in the German sequence, and both of them are being passed to the network to generate an output to compute. And that output is being compared to the target output to compute the loss. Yes.
Just to clarify, the labels, the ground truth is only used at the like computing the attention, the context, right?
Not no. Look, it's also being passed here.
Yeah, I mean that's
Those are so there are two things going in. You're passing in the most recent word and the context. Correct?
and we've used ground labels for basically calculating both.
The ground truth labels are being used to compute the hidden states. The hidden states are being used to compute the context. And the ground truth labels are also being passed in as the most recent word. Yeah. Okay, so now if I were to do this the traditional way, then the model would only get the input. The loss, the label sequence is not passed to the network. The label sequence is only passed when you're computing the loss, right? This would be the more traditional way of training a neural network. Why would this not work here? Yeah.
If it gets off at all early on, it's going to completely degenerate later in the sequence.
That's kind of there, yes. Evan?
Number of possibilities and so on.
It's not just the number of possibilities. When you just run this thing through the network, you have no control over what it's going to produce, right? You want it to produce, Aishaba and an Apfelgeges, and it just comes out with help me. So how are you going to compare these two to compute a loss? It's impossible, especially in the early portions of training. The output is going to be completely garbage. You're probably going to get run-on sentences 2,000 words long before you get an end-of-sequence marker, and your input is 10 words. Your ground truth label is 10 words. They are not comparable, which is why the maximum likelihood estimation procedure makes a lot more sense, because you have a one-to-one correspondence, right? So the maximum likelihood procedure ensures a one-to-one correspondence between the outputs and the target labels by actually providing the target labels also as part of the decoding process. But this doesn't match what you do during inference. There's a mismatch, right? So from the perspective of traditional training, passing in the ground truth labels as part of the forward pass is cheating in some sense, is it not? But then without it, we can't work. So is there a compromise between the two? What would the compromise be?
Mask like some parts of the ground truth label.
So exactly, right? There's a midway solution. I'm going to pass in the ground truth, but then every now and then there is one word where I won't just be using the ground truth label. I'll do the real thing. I'll sample the word from the output. And so over here, for example, this is the decoder. I'm going to give in the first 3 words is the correct one. For the fourth word, I actually drew a word from the output at time 3. But then the subsequent words are ground truth words. So you would expect that if the model were really, really good, you really wouldn't need to be feeding in ground truth labels on the decoding side, because it's going to get it all right. But then it's never going to be really, really good, right? So to control it, the fraction of words that you would be feeding in by actually doing performing the sampling process is going to be small, at least in the beginning. And even towards the end, you're rarely going to just do the traditional training. You're going to anchor it with the ground truth to make sure that things don't go haywire. Yes. Go ahead.
So Professor, here one of the reasons we are passing ground truth tables is to restrict also the sequence or the length of the output that we are producing.
It's not just the length, it's also the correspondence. You don't know what to expect, right? So when I give it the ground truth, it's like modeling language. I know exactly what word must be expected. And so I can compare that to my ground truth label to computer loss. Otherwise, if I've got like a 17 words of garbage, then which of the ground truth words must the next word be compared to? You have no idea. So the correspondence is also missing. Yeah.
But like if we for example passing the like incorrect words during the training process, then won't all the words generated like after that?
So the rest of them are still going to be the ground truth. So you're kind of forcing that one. At that point. You're sort of forcing it to generate the correct word, even if the fourth word were wrong, based only on the past and the context.
But then, like, we are trying to maximize the probability where the conditioning is like incorrect.
The conditioning is correct. The word
different from the ground truth, like the conditioning from in ground truth.
So the point is that you want to say that if some fraction of my conditioning input variable is wrong, I should still generate the correct output based on what I already have and the context. So that's, you're trying to make it robust to that. Any other questions? All right, yeah.
Differentiate the drawn words, the drawn outputs during propagation.
Okay, so sampling is not differentiable, right? Now, if you were to perform back propagation, then there is one place where the output is going back into the input. And so your back propagation would actually have to go back reverse up the black arrow. In the other places, because I'm providing the ground truth, there is no information from the output going back in. And it turns out that computing the differentiation across that black arrow is really painful. So we have something called the Gumbel trick, which is a reparametrization trick. It's drawing a random sample from a distribution is the same as adding something called Gumbel noise to the distribution and then picking the largest value. And picking the largest value is the same as max, which can be replaced by softmax, which is a differentiable process. So you can actually compute derivatives at those locations alone. It's complicated, but you'll encounter this in your homework. I won't spend time on it. Any other questions? Yeah.
Without knowing the encoder output, how will we be able to like?
The encoder output is always assumed known, right? The encoder, it's a training data. So both during training and inference, you have the encoder output, yes.
So the Gumbel noise is used when you're sampling from the models.
That's correct. Yeah. You don't need it otherwise. Why would you need it? Right? So, and there are various extensions because the encoder doesn't need, because you're encoding the entire input data. The encoder doesn't have to be left to right. It can be bidirectional. It can be right to left. So there are no restrictions on the encoder. And attention, if the input gets too long, then the entire attention formalism sort of can get very complicated, at least computationally. So there are various variants where you look at short windows and other such tricks. Now we're going to encounter some of them in your homework, so we'll leave that. There's also this other business of something called multi-headed attention, where instead of generating just one key and one value from the encoder hidden state and one query from the decoder state, you can get multiple sets of these guys. And so the idea is that maybe one set of, and so you get everything with a superscript 0 is going to be used to compute one set of attention weights and one context vector. Everything with a superscript of 1 is going to be used to compute a different set of attention weights in the second context vector, and so on. You can have as many of these as possible. Each of these is called an attention head. And the idea is that it allows the model to focus on multiple regions of the input at the same time and extract different information from these.
Here, only the values are being used. So what do we do with the keys?
The keys and the queries are used to compute the attention weights.
Oh.
Right? That's what we said. Okay? This is a two-eyed owl. Okay, 10 seconds, guys. All right. Somebody on Zoom, can you answer the first question? Nobody on Zoom?
The full tree search.
Okay, thank you. And the second question, is that first statement true? Second one? Third one? All right. So the optimal decode with an attention-based decoder would require a full tree search to give you the best, most likely, correct, most likely answer. In a query key value-based attention mechanism, the key and the value are not, it's actually the key and the query that are used to compute attention weights, right? You have multi-head attention computes a separate set of keys and values for each head at each input. And multi-head attention computes a separate query for each head at each output. So these were the key components. Now, any questions? There's some very nice results using this whole thing, but I'm going to sort of skip these results. If you've been using ChatGPT and such like, all of them are based on attention-based models, but then not exactly what you just saw now. We're going to take one step ahead. I'm going to spend the next 20 minutes on this. But here are some really nice, we saw some examples on English to French translation. But once you begin breaking things down into an encoder and a decoder, the encoder can be anything, right? And so here was a very nice one where they captioned images. And so the encoder output was actually the output of a CNN on an image. And you could pay attention and you can see how when you caption it, a woman is throwing a frisbee at a park. It magically learns to pay attention to the frisbee in the image. Yeah.
This might be a basic question, but when we do backtalk in this, do we do it through the encoder as well? Do we change?
Everything has to train, the whole model end to end, from the output to the input, including the attention module, right? Yeah. So, or a group of people sitting on a boat in the water, the attention is kind of highlighting the people, right? Or a giraffe standing in a tree in a forest with trees in the background. And if you look at the portion of the input that is high, that it pays most attention to, when it's generating the word trees, it's actually focusing on all of the trees and not on the giraffe. So it's really beautiful. And so a quick recap, we've looked at various forms of sequence-to-sequence models and generalizations of which are generalizations of recurrent neural network formalisms. Lots of papers, please look them up. And if you have questions, post on Piazza. And of course, just to make sure that, you really understand the subject, homework form. But anyway, so the recap is, going back, if you have a sequence-to-sequence model, the simple translation model was the simple one, where you had a recurrent network process the entire input, and then the final hidden state was passed to a decoder, which used the final hidden state to generate the entire output. This we said was suboptimal. So the next thing we did was say that instead of having the decoder look at just the final hidden state, why doesn't it look at every single vector on the hidden input side and compute some weighted sum of all of these guys, right? But once I begin doing this, then does it seem to you like the recurrent nature of the input is now required? You're actually looking at the entire input and you're learning, the model is learning to figure out which portion of the input it should focus on, right? So having a recurrent framework over here seems kind of redundant. So let's get rid of it. Okay, it's gone. But then, if I do this, I say I have a problem. What is the encoder doing? It's generating representations for all of the words in the input, right? But in doing so, for any mechanism, for any processing of the input, the representation that you're going to be generating for any input depends on the task, and it probably depends on things on the side. If you were performing some kind of sequence-to-sequence model, for instance, which was trying to perform part of speech tagging. Then the representation that it needs for any particular word depends on what the other words were. The part of speech for any given word depends on the adjacent words. Or over here, the representation for the word "an" depends on other words, because depending on what it is, "an" is going to be very different in German. So we're going to, how do I reintroduce this dependence on the input without explicitly having the recurrent structure in the network? I can do this by using the attention mechanism itself. So this is what we will call self-attention. Here's what we will do. For every word in the input sequence, I just compute an initial representation, isolated. Then from every one of these words, hidden representations, now I'm going to generate 3 vectors. One is a key, the other is a value, and the third is a query. So to compute the updated representation for the word H0, for instance, the 0th word, I'm going to use the query that I computed. So again, the key, query, and value are all just projections, different projections of the hidden state H. So I'm going to use the key of the 0th word, which is Q0, against the, sorry, I'm going to use the query of the 0th word, which is Q0, against the keys of all the words, including itself. So against K0, against K1, against K2, against K3, K4, right? And what this will give me is it's going to give me an attention, going to give me attention weights over all of the words. I'm going to use those attention weights to compute a weighted average of all of the values. And that weighted average is simply going to now be my updated representation for the word for H0. That makes sense to everybody, right? So I'm performing attention, but on the input itself. And in order to do this, instead of having the key, the query come from the output side, the query is being generated at each point within the encoder itself. That's all it took. And now I could use the query and the keys to compute attention weights for everything. And I could use these attention weights to compute a weighted average of the values. Yes, yes, sir.
I don't get how this differs from what we were doing before.
Pardon me?
I don't get how this differs from what we were doing before.
So what we did before was this, right? The queries came from the decoder side. Okay. So earlier, this is what we had. If you go back, a simple one. You're making me go back way back when, see?
No, I understand.
So you see what was happening over here.
I don't understand what you added in terms of.
Okay, so how many vectors are you extracting for each H on the encoder side?
Key and a query, aren't you?
Okay, and so now when I do this, how many am I extracting?
What's V0 in this case? So what's the value?
So H0 is being projected to V0 by multiplying by WV, right?
Okay.
We have these 3 projections over here.
Then how are we using the value?
So how are we using the value in the previous attention framework? We were using the key and the query to compute attention weights.
Yeah.
And the attention weights were what we were using to compute the weighted average of the values, and that was the context, remember?
So you're also just saving the output values from each entry.
So at each point, you're going to be computing a value vector, V, this is a vector, a key vector, K, and a query vector, Q, by applying the 3 different matrices, W, Q, WK, and WV, right? And so now I can compute a inner product between this key, this query, and this key, between this query and this key, between this query and this key, and so I'd get 5 different inner products, right?
Well, I guess my question is, where do you use the value?
Pardon me?
Where do you use the value that you calculated?
Let me finish, right? So if I compute the inner products, I'm going to get 5 inner products. I can use those to compute 5 attention weights, right? I can use those attention weights to average the 5 values. Like so. Like so. Right here. And so that's going to give me my updated representation for H0. That make sense?
Kind of.
Okay, anybody else confused about this? Anyone? Thomas?
Yes, but.
Okay, so where did I lose you?
Well, I think I just need to go back.
Okay, so here is what I'm doing. I'm going to run back, run over a few minutes because this is kind of key, right? So here's what I've got. I have H0, say H1, H2. Let me just use 3 of these guys. Then using those 3 different projection matrices, I get Q0, K0, and V0. All 3 are vectors. Then I'm going to get Q1, K1, and V1, Q2, K2, and V2. So are you with me so far? Okay, this is easy, right? Then I can say G1, I'll call this G00 is Q0 times transpose times K0. You still with me? Okay, G01 is going to be Q0 transpose times K1. G02 is going to be Q0 transpose times K2. This make sense? Okay, so I've used this guy against each of these 3 keys and got 3 raw attention weights. And I can always say W0I equals softmax G0I. So I can just go over all 3 and perform a softmax and get 3 weights. You with me still? Okay. And so now I can use these 3 weights, W00, W01, W02, and multiply these three value vectors by each of those 3 weights and sum them up. And that's going to give me a new representation of 0. That makes sense? Okay. Now to compute the same thing for this guy, this is going to become G10, where now I'm going to be using Q1. Correct? That makes sense to everybody? And so I'm going to get a completely new set of weights. And from those, I can use those weights to compute the weighted sum of all of my value vectors. And I'm going to get an O1 for this guy, and an O2 for this guy, and so on, right? So is this process clear to everybody? Yeah.
What is the intuition behind having like a different query and a different key? Like in this case, like can we combine them into like let's say a single vector and do the dot products?
Then you'd just be looking at the similarities between the queries and the keys. So the similarities between words. So if all of them were the same, then the attention weights would become symmetric. The weight that 0 pays on 3 is going to be the same as the weight that 3 pays on 0, wouldn't it? You don't want that, at least the raw weights. So you separate the 2. Any other questions? Okay. Now it gets into a bit of engineering. That whole block is what I will call a self-attention block. And in fact, I can have, this is a single head self-attention block. I can have multiple such heads, within each of which I'm going computing a different key value query combination. And so from each of those, I'm going to get one vector O. So this would be multi-head self-attention, all of which can be patched together into a single output for this multi-head self-attention block. And so again, the engineering is this one is finally put through an MLP, these vectors. And so that's going to be your multi-head, that entire thing with multiple heads of self-attention where the outputs are combined and put through an MLP is called a multi-head self-attention block. And you can have many such of these, one on top of the other, to compute your final output, right? So this still ignores relative position. The fact that H2 is ahead of H0 is not being considered. They're just sort of comparing themselves to one another, but positional information is lost. So
do H0 to H4 have the same weight matrices? Is there parameter sharing happening?
there's no, the weights are the same within any attention block.
Okay.
Yeah, so And so to account for position, we're going to do one more thing. Note that the inputs are actually word embeddings. So we're going to add a positional encoding to them to capture the relative distance of one to the other. So we want to say that I'm going to add to every input embedding, I'm going to add a vector which is unique for that position. So there's a specific vector which will only occur at the 0th position. There's a specific vector which only occurs at the 1th position, and so on. That's easy enough. I can just generate them using a random vectors. Because if I generate random vectors, these are going to be unique at each position, but they still don't capture relative position. So we're going to impose an additional constraint on them. I'm going to say that if I take any position vector at time t and the position vector at time t plus tau, the relationship between the two is a linear relation that only depends on the time difference. And so the relation between P1 and P4 is going to be the same as the relationship between P7 and P10. And that's going to be given by M3, right? So now how can we generate a positional vector of this kind? It just turns out that there's one possible solution. It's on the slides. If they use a trigonometric relationships to give you this positional dependence. I won't go through the actual equations, but that's what the sequence of position vectors looks like. They never repeat, and you have exactly this behavior. And so this sequence of positional vectors actually gets summed up with the input embeddings to burn in positionality. And the rest of this is just what we just spoke about. And so finally, when you have several such blocks, you have an encoder which uses no recurrence at all. But it has successfully managed to capture positionality. It has successfully managed to capture relationships between words and yet obtain an embedding for every word that is unique. And this entire collection can be passed to the decoder. Yeah.
So is H0, H1, and so forth, are those just the word embeddings plus the positional vector?
At this point, yes. I mean, you could have the positional embeddings being added at any point, but in this case, yes. Yeah. Yeah. Yes, Ronnie? Yeah, okay. Thank you. We'll get to that, right? So this is the self-attending encoder where the recurrence has been replaced by self-attention. Can we use self-attention to replace recurrence in the decoder? And the problem with using self-attention is that you're computing a weighted sum of everything, right? Including things in the future. But the decoder is a autoregressive model. It's taking the latest word to generate the next word. So you can't actually use this basic self-attention model for the decoder. So what we will do is to change it slightly. Here's what your standard self-attention was. To compute the representation of, say, ST, you computed a weighted sum of all of the hidden states, right? Or the values from all of the hidden states. In the decoder, to compute the hidden state, the next value of ST, you're only going to use everything until then, but not the ones in the future. So this is what they call masked self-attention, in that you can still just use the same arithmetic and compute the weights, but then everything in the future is going to be masked. And so this makes it a causal process. At any time, you're only using those vectors and things in the past. But the rest of it is the same, right? You can have a multi-head masked self-attention and an MLP to give you a output. And so there's a multi-head self-attention and an MLP that gives you a masked multi-head self-attention block, which is autoregressive, meaning this block, when you're computing the kth output, the kth output is only going to be a function of the first k minus 1 outputs and not everything in the future, anything in the future because of the masking. Now this makes the whole process more expensive because you'd have to repeat this computation every time you generate a new output. Whereas on the encoder side, you had no masking and the mask didn't change. So you just did it once, right? Yeah.
Why do we need self-attention then? I mean, what is the problem with having recurrence in the network?
If you want to replace recurrence, this is what works, right? You're absolutely correct. Why? The answer is because it works, right? And so this is your entire decoder process. A lot of what we are talking about is like one full semester of me telling you this works. I'm sort of forcing science into it, but really it's just this works. Anyway, so here's your third poll. Please wait the extra 3 minutes. We'll wrap this up. "15 seconds, guys. We're running out of time. Actually, I'll save myself 5 of those seconds. Time's up. So, which are the ones that are true? The first one, self-attention computed for an n-length input requires the computation of an n cross n attention weight matrix for each head, right? Each head is going to be computing the attention of every word against every other word on the encoder side. The rest of it is just false. Okay, I'll skip that. And so this was this famous paper, the transformers, the attention is all you need by Vaswani et al. In 2017, which is the basis of pretty much all of the large language model works that you are seeing these days. And so the next, there was some, back then they showed that the simple model with no recurrence was matching many of the state-of-the-art models at a fraction of the computation cost, because recurrence is slow and self-attention, even with masking, is much faster. So they actually got orders of magnitude speed up if you actually look at the training cost. And now this has an encoder and a decoder. Now this was what was first built, the encoder decoder model. But then we know something from what we've learned so far. What is the decoder, basically? What was the decoder? It's just a language model, is it not? The decoder was performing conditional generation. If you got rid of the conditioning, if you got rid of the context vector, this is just a regular language model. It's going to be generating words, right? Word sequences. And we got it to condition based on the context that it got from the encoder side. So now when you actually use this complicated self-attention model, with the mass self-attention model, and then you throw away the encoder entirely, what are you left with? Just a language model. That's your GPT, right? That's your every version of GPT. When you go on GPT-4, when you go on Google Bard, you're basically using just the right column. So similarly, if I just focus on the input, what is the input doing? The input is generating meaningful representations of the whatever input sequence you give it. It is also a mechanism for generating meaningful representations of language if the input is a sequence of words. And so you had these two different mechanisms. The first was BERT, which only looked at the encoder of the transformer to derive word and sentence embeddings. And the way you did it was to train it to fill in blanks. You give it a sequence and you say, what is the 7th word? I'm not giving you the 7th word. And many variants of the basic task. And they showed that the representations that you get from this basically result in large improvements in performance in many NLP tasks. And GPT, of course, we know how it works, right? So self-attention can effectively replace recurrence and sequence-to-sequence models. This is what gave us transformers. The use of positional embeddings is encoding is kind of key. Without it, the whole thing doesn't work. So there's been a lot of work on how to compute the most effective positional encodings. You can learn those, for instance. And they can be used in regular sequence analysis setting as a substitute for recurrence. And obviously, it is the state of the art in pretty much everything you're going to encounter. So I'll give you a final poll, and then we're done. I can't leave you without that final poll. If I spent a little less time searching for the chalk, we'd be done on time. So, okay, time's up. Which of these are true? A and D, right? BERT is the encoder of the transformer model, and GPT is the decoder. And there's been work on vision transformers. You can chop up inputs, images to little blocks and apply the transformer model here. Lots more stuff. I'll stop here. Thank you.
Steve.